Originally, my plan was to make another video on AI news where I summarize what has happened in the past week, but somehow everything that I found seems to vanish in terms of importance and relevance compared to AlphaEvolve by Google. AlphaEvolve is a self-improving coding agent which, among other things, discovered a new way of multiplying matrices and improved on the state-of-the-art of that calculation, of that process, that we were stuck on for the last 56 years. It also improved circuit design for TPUs, which are used to train Gemini models, and it also sped up the process of training Gemini models by 1% by improving a heuristic. This seems like one of these huge milestones, which is why we're going to talk about it today. So let us get right into it. There it is, AlphaEvolve, a Gemini-powered coding agent for designing advanced algorithms. This is the article published by Google DeepMind, which summarizes the white paper, or at least the achievements of the white paper. Down here you have a link, AlphaEvolve, to the paper that we're going to take a look at. And this video today is not going to be a super technical deep dive in terms of we're not going to discuss every single point mentioned in the white paper. However, I do want to take it a little bit deeper than a lot of the videos that I've seen on YouTube. We're not just going to discuss briefly that it's a self-improving coding agent and that it somehow improved on matrix multiplication and hardware design. But I want to show you also what it looks like behind the scenes. Now, behind the scenes means what is shown in the paper. I cannot show you anything that's not in the paper. But I want to discuss that a little bit and explore the details of how it works. But yeah, by reading through this article, you can already see what this is about. You can see that it is about evolutionary algorithms, or an evolutionary approach for designing better algorithms using large language models. And the achievements here are optimizing the computing ecosystem, improved scheduling, which I talked about, hardware design, which I talked about, and also down here I think it mentions the matrix multiplication outperforming. So it outperformed the Strasson's algorithm, I think it's pronounced, 1969. So for 56 years, no improvement, and now it found an improvement, at least for certain types of matrices. That is like the summary. And what I want to do in this video today is take a look at the white paper. And this is going to be unscripted. I'm just going to scroll through it and talk about the points that I have highlighted here. I read this paper myself today, or white paper actually. And I want to just cover what I think is interesting here. So AlphaEvolve, a coding agent for scientific and algorithmic discovery. Here you can see the abstract. It's always the best starting point when reading a paper or a white paper, doesn't really matter. And you can see the key points are it's an evolutionary coding agent. For those of you who don't know what evolutionary algorithms are, or genetic algorithms, I have a video on my channel, but the basic idea is you generate solutions, you mutate them, you combine them, you iteratively improve, and you have an evaluation function, a fitness function that tells you how well your approach works. And then you basically take approaches that work well, you multiply them, you mutate them, you reproduce them, and so on. It's not the exact same thing here with AlphaEvolve, but the process is similar in terms of it generates candidate solutions, and it generates also prompts and everything, and then it compares them in terms of effectiveness, and then basically like that iteratively it improves on solutions, or in terms of algorithms that generate solutions. This is also a different approach that they take here, but you can see what I highlighted here is evolutionary coding agent substantially enhances capabilities of state-of-the-art LLMs, and the idea is that it orchestrates an autonomous pipeline of LLMs. So we have multiple LLMs working together. To be precise, we have Gemini 2.0 Flash models and Gemini 2.0 Pro models. So 2.5 is not even used here, which means it can get much better if we take the currently best models on the market, of course. But the basic idea is this evolutionary approach. What we do is we define so-called evaluation function, or evaluators, and then the program iteratively improves on the algorithm, always getting feedback from the evaluators. This is also a limitation of this, that we can only use this approach for problems where we have an automatic evaluation function. It doesn't work with anything else, because the process is, in order to automate it, you need to have automatic evaluation. It doesn't have to be quick. It can be very complex evaluation, but it has to be evaluation that can be done without humans, can be done mathematically, and produces scalars, essentially. So yeah, what it does here, the results, it developed a more efficient scheduling algorithm. It found equivalent simplification in the circuit design of hardware accelerators, and it also accelerated the training of the LLM underpinning AlphaEvolve itself. I think this is also something that has to do with a kind of matrix operation. I have highlighted something below that we're going to take a look at. And also, this is probably the most famous one that you have already seen on YouTube quite a lot, which is it developed a search algorithm that found a procedure to multiply two 4x4 complex valued matrices using 48 scalar multiplications. Now, two things that are important here. You can see it developed a search algorithm that found a procedure. It didn't find a procedure directly. It implemented something that found the procedure. So this is also how AlphaEvolve is being used sometimes. And the interesting thing about these scalar multiplications, I think the previous record was 49, is when you do matrix multiplications, additions are basically free. You want to focus on minimizing multiplications because that's where the computation happens. So if you can reduce the number of scalar multiplications, this is what you want to do to get to better matrix calculations. And this is the first improvement after 56 years over Strassen's algorithm. Now, I'm going to be honest, I don't know this algorithm and I don't know what the improvement is. And we're not going to take a look at that because I'm not interested too much in the findings or in the improvement of the state-of-the-art research. I'm interested in the technology AlphaEvolve. But this is super impressive because faster matrix multiplication is oftentimes very useful in the context of deep learning. Now, let us move on to the introduction. As it says here, AlphaEvolve focuses on the broad spectrum of scientific and engineering discovery problems in which the candidates of discovery can be automatically evaluated. This is the key point here, can be automatically evaluated. As I said, this only works if we can provide an evaluation function so that the LLM pipeline can make adjustments, do some changes, try something, and then evaluate it to see if it did something useful or not. This is super important, otherwise there's no automation. Then we have here the LLM directed evolution process is grounded using code execution and automatic evaluation. Yeah, basically what I said. And then here, this is the key point that I was referring to before. It is applicable both to problems where discovering new algorithms is the intrinsic goal, as well as to the broad range of problems where the solution of interest is not an algorithm itself, but an algorithm can describe how that solution is to be constructed or found. So basically, you can use AlphaEvolve to find the solution, to find an algorithm itself that is useful, or you can find algorithms that give you solutions similar to what's written here. And then it says here, it turns out to be a surprisingly effective strategy compared to searching for the solution directly. This is also what we did with the matrix multiplication, or what they did with the matrix multiplication. Then here, just a quick mention. I don't know if that's interesting to you guys, but there has been something similar, which is FunSearch. I don't really know about it, but it's an LLM-guided evolution to discover heuristics. It's not even that interesting to look at FunSearch, I guess. It's interesting to see how AlphaEvolve is different in terms of it can evolve entire code files, not just single functions. It can evolve hundreds of lines of code. It can use any language, any programming language. It can do this evaluation process for hours. It benefits from state-of-the-art LLMs. It's not limited to small LLMs. It has a lot of context and feedback embedded in the prompts. And we can also optimize multiple metrics. So it's not like we have to say one metric has to be optimized. We can have this on a multi-dimensional spectrum, and we can simultaneously evaluate and improve in terms of multiple metrics. And down here, they also highlight again the limitation that I talked about, that we cannot do that with tasks that require manual experimentation. So it only works with automated evaluation. And so again, to repeat, in math, they consider multiple problems. Interesting here, this is a lot of problems that are maybe not that useful straight away when you just look at them. So how many circles can you fit into a certain space, into a square, I think, or into a rectangle, I think square. And how can you maximize the radius? So stuff like that. I think it's also something like the kissing circles, where you have basically the circles and how many shapes can touch it or something like this. Some mathematical geometry stuff. And the interesting thing here in terms of the AI is that it matched the best known constructions on around 75% of them. And also interesting here, in many cases, these constructions are likely to already be optimal. So maybe it didn't find anything better because they already are the best solution. And on around 20% of the problems, AlphaEvolve surpasses the state of the art and discovers new, provably better constructions. So this is super impressive. This is an AI system, an AI coding agent that outperforms the state of the art, the best things that we know have been discovered in certain problems by humans. Now, to be fair, we need to put this into context here. Matrix multiplication is interesting, but with a lot of these problems, maybe not so many people are working on them. And also, when we look at the solutions, some of them have very specific solutions that a human would never find, except with brute force. So maybe some of these problems are just not optimized, or maybe we haven't found the optimal solution because humans haven't really tried that hard. But nevertheless, it's still impressive that AlphaEvolve can improve on the state of the art itself, on its own, basically. And this is now where we get to the interesting part, AlphaEvolve itself. So this is now the architecture and how everything works. I have a bunch of things highlighted here. I'm going to try to explain it in a simple way. But basically, the orchestrating procedure is an evolutionary algorithm that gradually develops programs that improve the score on the automated evaluation metrics associated with a task. Here you can see a basic illustration. The basic idea is the human defines what has to be done. So the human sets the evaluation criteria. The human also provides an initial solution. Now, this initial solution can literally just be return something. It doesn't have to be meaningful in any way. It can just be any solution. And then also optional background knowledge. And this problem definition is fed to AlphaEvolve. And what AlphaEvolve does now with this problem definition is it improves on it. How does it do that? It crafts a prompt. This prompt contains context. And if it's not the first iteration, also past trials and ideas. Then we feed that to an LLM ensemble, Gemini 2.0 Flash and Pro. They propose changes of improved programs. So they propose improved programs. These are then evaluated by the static or by the deterministic evaluators. So by the thing that is provided by the human. And then what's happening is that a certain program database is being filled based on these scores. So this is now our knowledge base, past trials and ideas and suggestions with all the metrics associated with them. And then in the next iteration, the prompt sampler does the same thing again, but it includes examples that are in the database. For example, it can do something like, look, this kind of improvement worked well in the past. This is the score that we got with that. Then this improvement also looks interesting. Try to find something similar or try to improve even further. And all this is powered by the evaluator. So this is basically the quality metric. We get something in the beginning. We get suggestions from the LMs. This here serves as a filter to tell us, okay, is this actually a reasonable improvement? And then we fill the database and then we retrieve whatever we think is useful for the next iteration. That is how it basically works. So yeah, the user must provide a mechanism for automatically assessing generated solutions. This is a function H mapping a solution to a set of scalar evaluation metrics. So we just take in a solution, a proposed algorithm, and we get our metrics, 1 metric, 5 metrics, whatever. And that is being used as the basis. Now here we have a more detailed illustration, which is how it basically works here in pseudocode, or actually maybe with actual code. What we have is, again, the prompt sampler, and here we see that the loop is the following. We get a parent program, we get inspirations. So these are retrieved from the database. We sample from the database some inspirations and the current program. Then we get a prompt, which is built by the prompt sampler. So this prompt sampler takes the parent program, it takes the inspirations, and crafts a prompt that instructs the model to improve. Then the LM generates a diff, so it generates changes in the code, so it makes changes in the code. And then we get a child program by applying the differences to the parent program. So we do whatever the LM asked us to do. We take that child program, we execute the evaluator on it. So we evaluate this child program, and then based on the results, so based on how well it performed, we add that child program to the database with the respective metrics, and then it's going to be retrieved or not in the next iteration of this loop. So again, to keep it simple, we get from the database what we need, inspirations, past trials, and so on. The current program, we craft a prompt, we get improvements or at least changes from the LLM, we apply them, we evaluate, and we add the results to the database. And by doing that, AlphaEvolve improves on our code. Yeah, so I think this is basically what we talked about here. Then, interestingly, how does this look in code? The basic idea is that we specify blocks of code that can be annotated, or blocks of code can be annotated as to be evolved by the system. This is done with comments like evolve block start and evolve block end. I think there's also an example somewhere down below. That is basically, maybe we can scroll down. This is basically what it looks like. So that would be the input A. We have evolve block start, evolve block end, evolve block start, end, and then we have the evaluation function, which is not going to be evolved. And essentially what it does now is it provides an example. So I think B is the prompt. Yeah, so we basically start with this. We feed that into AlphaEvolve, and AlphaEvolve produces this on the right. So AlphaEvolve crafts a prompt basically that says, act as an expert software developer. Your task is to iteratively improve the provided code base. Then it says prior programs. Previously, we found that the following programs performed well on the task at hand with these metrics, and then the code that was created. And then you see the current program and the metrics, and then it says, okay, make sure the changes you propose are consistent and so on, and then suggest a new idea, blah, blah, blah. And then as a result of that, we get something like this, where we have search, replace. So basically take this from the code and replace it with this. Take this from the code and replace it with this. So in this case here, what happens is it adds more layers to the neural network. I think this is like a convolutional neural network. And basically it adds more layers, and it also changes the optimizer from Atom to Atom W with weight decay, and that hopefully improves the program. And that is how this looks in actual code. So this is actually what you pass. You pass something like this. This is the prompt that's being crafted, and this is what you get as a result, and that is then applied and evaluated and saved into the database. So as you can see here in the icons, this is 1, 2, 3. This is the steps that we saw above. 1, or actually, yeah, 1 this here, 2, 3. And then you would do evaluation and program database. So then let's take a look at flexibility in choosing the abstraction. Basically here it says we can evolve in different ways. So for example, we can use the classic way from genetic algorithms to directly evolve the solution, the string representation of the solution. So to directly do the evolutionary process on the solution representation itself. Or we can evolve a function of a definite form that specifies how to construct a solution from scratch. So you construct a function, the function constructs a solution. Or you can also use search algorithms here, or you can co-evolve intermediate solutions and search algorithms together. So a mixture of these approaches. Then to the prompt sampling, how is the prompt crafted? Basically, it supports various types of customization, so we can provide a lot of context here, samples from the database and instructions and all that, explicit context, so equations, code snippets, PDF documents, also stochastic formatting. We can have template placeholders. We can also include evaluation results. We can also evolve the prompt itself. So we can do prompt evolution, which is also something that we're going to see down below. Everything that they do here makes sense, because if you take certain things away from the process, it performs worse. So all of the things that they do here are useful and actually improve the performance. Now, another thing that's interesting is here in 2.3, they mention AlphaEvolve performs increasingly better as the underlying LM improves. And this is cool because right now, as I mentioned, they use Gemini 2.0 Flash and Pro. They don't use Gemini 2.5 Flash and Pro. So that is also something that shows us there is more room for improvement here. Here you can see it down below, models used, Gemini 2.0 Flash, Gemini 2.0 Pro. And they also say here that the mixture is very nice because Gemini 2.0 Flash has lower latency, so it has a higher rate of candidate generation. It's going to explore more quickly, and it's going to do more stuff that is maybe not as high quality, but it has this exploration capability. So find different kinds of solutions, and then Gemini 2.0 Pro focuses more on higher quality suggestions, takes more time, and this strategic mix optimizes the overall process. Now, in terms of evaluation, they also say that they have more than just using the function H, so just using the evaluator. There's also evaluation cascade, which is like a hypothesis testing approach where you have the test cases and they get more and more difficult. And basically what you do is you let the algorithm solve easy problems, and if they fail, you already prune them out. So you basically just focus on those that are obviously not faulty, and you increase the difficulty. And by doing that, you don't have to evaluate all the models equally. You just focus on the ones that seem promising. Then you also have LLM generated feedback. So for certain things that are not so easy to capture with mathematics and with deterministic algorithms, we can also get LLM generated feedback, and there's also parallelized evaluation. And now I think we get to the interesting part, which is the results. So now we can see what exactly has happened as a result of AlphaEvolve. And again, I'm not going to focus too much on the technical details of these individual problems or individual solutions rather. But one of the most talked about is the faster matrix multiplication via finding novel algorithms for tensor decomposition. I'm not going to talk about this too much, but the basic idea is this is the best known that we had before, scalar multiplications. So you can see this is the number of scalar multiplications required to compute this matrix product. This is like the world record that we had, and now AlphaEvolve comes along and solves some of them. So you can see here for these, AlphaEvolve improved. This is the one I think that is mentioned as the showcase. So 48 instead of 49 scalar multiplications. And this, of course, makes a difference at scale. We also have here search algorithms for a wide range of open mathematical problems. Now, this is interesting because here we have a graphic showing some of them. I don't know most of these or any of these actually. This is the one I talked about with the circles. The basic idea, if we zoom in here a little bit, is that you want to fit all these circles into a square, and you want to maximize the sum of radii, which is the plural of radius. And this is the one that I wanted to mention. It's like the values, if you look at the details, the values here that were chosen are so brute forced computationally. The improvement is not very large, but we have an improvement. But they're so brute forced computationally that a human would probably never think about these. Whereas the best solution up until now had pretty elegant and equal radii, I guess. So that's something to keep in mind. You can brute force a lot with computation, whereas a human will try to find more elegant and easy solutions. But yeah, you can see improvements on all of these mathematical problems. Now, what did we do here? Figure 4, these changes are highly non-trivial. Oh yeah, this is basically the thing that led to the matrix algorithm being improved. I'm not going to pretend like I understand this, so not much to say about this here. But if you're interested in that, you can look at the details. Also, I think in the appendix, you can see the full output. But yeah, basically, it was all about evolving heuristic search algorithms and not evolving the constructions themselves. So we're not evolving the solutions, we're evolving the algorithms that produce the solutions. This is what they did here. Another thing, this is interesting, they optimized Google's computing ecosystem. They found a way to more efficiently schedule compute jobs, and they did this with this simple function here. This is the heuristic function discovered by AlphaEvolve that assigns a score. I have a note here, basically a ranking function. The question that we ask here is, given the current state of the machine, how well does this workload fit? So you have a required CPU and memory value for this task or for this job, and then you have the available resources, and then you compute these residuals here, and then you apply this formula, which results in this heat map here. And basically, it improves in terms of which task you choose. You choose the task with the highest score, with the best score, and then you schedule that, and this leads to performance improvements. And I think it mentions it somewhere, on average 0.7% of Google's fleet-wide compute resources, which, to be honest, in terms of Google is huge. 0.7% of resources of Google is crazy. This is not a small number. Then we have some matrix stuff here that, to be honest, I don't really understand, but essentially they have kernel engineering here for Gemini. So the Gemini models are built on JAX. I have a JAX video on my channel, so a brief introduction into JAX. And then we have Palace, which I don't know about, but it's an extension to JAX, and it enables writing custom, highly specialized programs, also called kernels. And one critical aspect of these kernels is matrix multiplication, and dividing a large matrix multiplication into smaller subproblems. And how you do that essentially is not trivial. And yeah, basically AlphaEvolve improved on that and discovered a heuristic that led to an average 23% kernel speedup. And if you take that into account, then you get roughly a 1% reduction in Gemini's overall training time. And this significantly reduces the time needed. Then also for the circuit design, basically, it improved on Verilog code. Verilog is a hardware level language, And it found something, as far as I understand, that is essentially equivalent to what they already had, but it still found it itself, which is impressive. I'm not really that much into hardware and circuit design, so I don't really know what this is about, but it seems like it had also some pretty impressive results in that field. And then it also directly optimized compiler-generated code, leading to a 32% speedup when it comes to flash attention, and also here in the pre and post processing, 15% speed up in that part of the process. Now we get to something very interesting, which is ablations. I didn't even know that word, but basically it means you take away stuff from the system, from the agent, and you see how well it performs. So what they did here is they had this matrix multiplication, tensor decomposition problem, and also the kissing number problem. And the cool thing is, especially in the left illustration here, in the left graph, you can see how the model performs in green when you use everything that we discussed, the prompt evolution, so evolving the prompt itself, meta prompt evolution, using small LLMs, or using the full file, or not providing any context, not using the full file evolution, using no evolution at all. And the interesting thing is that green is like the best thing, where you have everything combined. And then whatever you take away, you can see that the performance drops, which basically means that none of these things is irrelevant. None of these things is useless. Everything that we see here has something that it contributes to the result. Now, evolution itself seems to be the most important one, because if you take that away, you radically drop in terms of performance. But even if you take something away like meta prompt evolution, this reduces the performance. So all of these things are important and a relevant part of the system. This is what this graph basically shows here. Here it says it again, as can be seen, each of the components is responsible for a significant improvement in the results. Then I think that's it for the most part. They have some stuff about future things that they can do. Essentially, there's the limitation of the automated evaluator. Yeah, obviously. But I think overall, this is a very interesting paper, a very interesting agent that they released. Unfortunately, I don't think it's anywhere public so that we can use it. But it's very powerful, and it gives me the science fiction vibes of the AI improving itself. This is a first step into that direction. I wouldn't say that we're significantly closer to actual AGI, but this is super interesting. Let me know in the comment section down below what you think about it. So that's it for today's video. I hope you enjoyed it and hope you learned something. If so, let me know by hitting the like button and leaving a comment in the comment section down below. And of course, don't forget to subscribe to this channel and hit the notification bell to not miss a single future video for free. Other than that, thank you much for watching, see you in the next video, and bye.